Stefan. Yeah, it's great, really great to be actually in this audience. As Stefan already told, I'm looking at representation learning and what it can bring to data systems. You're probably thinking, oh, there's missing a word, but fortunately, this is what binds us together here. I'm actually focusing on tables. And normally, when I go to ML conferences, for example, I have to convince everyone that tables are actually something different than natural language. But here, today, I don't have to do that. So I'm really, really glad about that. So I've been actually really focused on like downstream applications, but I'll try to also bridge two architectures of data systems. Promised. But first, let's think about the impressive capabilities that we've all seen, right, already, of transformers. And transformers is like the main architecture of neural networks that have made things really scalable. For example, creating funny dogs or funny images of dogs. You've seen probably also that it can generate text, right? So ChatGPT really helped me well to generate my graduation speech. But also it can complete our code, which is already a step closer to our world of relational database systems. So that brought me to the question, what about tables? And you might think, we have LLMs, so why would we even care about tables, right? Why not just analyze dogs? Not dogs, but dogs. Sorry. Well, I think Andy actually touched on that. Tables really dominate the data landscape. So if you consider the ranking scores of database management systems, you can see that the relational DBMS is actually most popular as a score. But also, if you consider data in the wild, for example, through Google dataset search, you see that actually the majority of the data is structured in the form of tables. You can think of CSV files, for example. So I think, tables, they are just available. They are there. And we can use them because they are full of fresh, structured, and domain-specific data. So there's lots of value in using that data, of course. And I think this is often overlooked by typical ML researchers. But actually, structured data, they really serve high-value use cases as well. You can think of, for example, data analytics, right? So I think we've seen many data systems here, and many are actually focused on analytical queries. So there are many tables and many tasks to be done. Now, we've been really focused here on storage, right? But that's actually the beginning. There's a whole pipeline that comes afterwards. And this is actually what I've been mainly obsessed about when I was a data scientist myself, actually. So there's retrieval, processing of data, you need to analyze it. And then, somewhere down the line, you actually also use these insights. But this is really a long pipeline, and every step involves so many different tasks. So why not shove an LLM into any of these, right? I think that's the whole holy grail that we're working towards. And today I will also discuss of some of those applications and show actually the power of LLMs for some of these already. But of course, I'm a researcher, and I also like interesting challenges. And the nice thing about structured data is that they are super rich and challenging to work with, especially with neural networks. Because tables, they come with such a diversity when you consider, for example, the dimensions, so the number of columns, the number of rows, etc., but also in structure. I know that relational databases have this very strict structure, but it's wild to see what people actually try to put in tables and how they do that. But you can also think about the cleanliness, right? What do we actually find inside that data? What is it actually about? It's lots of mess going on there as well. But they are also super diverse in terms of semantics, right? I think Andy touched on that as well. What is that data actually about, and what can we do with that? So here are a few examples. Of course, we like to see tables that look a little bit like the table on the left, but spreadsheets, for example, are of course also tables, so we need to also deal with that. So lots of weird hierarchical structures, etc., even visualizations included. How do we read that data then? So the goal of table representation learning is to map tables to some consistent input. You can think of a vector representation, and then try to learn some relationship between that input vector, that is a table somewhere upstream, and try the relationship between a table and different tasks. So tasks you can think of, the tasks that we've seen before, can be in storage or retrieval or data transformations and whatnot. Today I'll first talk a little bit about the power of table and particularly column semantics. And then I'll move on to actually the challenges that we see that we need to tackle to make table representation learning work. But I'll end on a positive note and then talk about how we can move towards end-to-end data analysis systems. So starting about the semantics and why that is so powerful for also data systems. So if you want to automate any task, you really need to understand what's actually inside that data. And a very important source of understanding comes through the columns of these tables, right? So what we want to do is to detect the semantic column types, so not the atomic types that you're used to, so integers or whatever, but the semantic column type. So what is it actually about? And so here we have an example table. You want to basically figure out, oh, that first column is a name, a salary, and then the thing afterwards, CNTR, is an abbreviation of a country. And that looks very easy, but very often these column names are just really not descriptive. So it can actually be a very hard task there. But as I said, you can also encounter many, many messy values inside these tables. So it's quite hard to then map that to a consistent representation. So assuming that you have figured it out and you found that good representation that captures the signal of your downstream tasks, what can you actually do with it? Well, some of these things you can see here. So you can, for example, inform on joining tables, so finding joinable tables in data lakes, for example. But you can also automate some data processing tasks, like capitalizing the first letter in names, because that's a more consistent. And that's actually where we started at. If you know the semantics of these tables, you can actually try to recommend visualizations that make sense for the data that is inside these tables. So that was actually the starting point of this whole semantic column type detection problem. So what we did, and this was back in 2019, so we did not have ChatGPT, right? So we informed this very basic neural network, because what we had at that point to do semantic type detection is regular expressions, which means we had a regular expression to, for example, find whether the values in a column were credit card numbers. Works very well for credit card numbers, but not for anything else that doesn't follow that structure, right? So that was basically what we were trying to do then. That was not robust, that was not scalable, and that very often also wasn't accurate. So, we took a different approach. Very, convoluted page here, but the bottom line is we took lots of tables that were labeled with column labels, and then trained some neural network on it to predict the types. For example, location, name, year, etc. And this worked actually surprisingly well. If we compared that to, for example, regular expression matching, which is obviously very poor in performance over way more types than credit cards, for example. It already reached an F1 score performance of 0.90. You can forget about the meaning of F1 score, but it's basically a balance between precision and recall. I think the main important thing is that these machine learning-based approaches on top perform way, way better than any string-based, value-based matching that we had so far. So for example, with regular expressions. So that was already really impressive to us, and it was pretty useful. But of course, there are many challenges because in tables, as I said, you have like lots of weird values that also neural networks, particularly fueled by text embeddings, didn't really work well with. For example, numbers. And I think that's one of the big differences between unstructured data and text and tables in relational databases. You really have to deal with numbers. So how do we do with that? But there were many, many other challenges, of course, as well. Well, you can, of course, think, okay, but you have not just one column, right? You have a full table. Why not learn from that? Okay, so we extended this column-based representation to a more table-based representation. And indeed, by incorporating also the neighboring columns, you were better able to figure out the meaning of one column. Makes sense, right? But that also helps a neural network, of course. We did some other additions to this or extensions by making it also adaptable, because in practice, you might have in a company a very specific type that is not known to a model that was trained on another data set. Well, we generated some training data for that type, and then we're able to adapt this pre-trained model, let's say, to those new types as well. Very impressive, looks cool. But of course, I can hear you think, what about LLMs? Don't we have, ChatGPT? Why would we even care about this, right? And that's actually pretty funny, because there have been many people actually, that try to pre-train table or LLMs also on tables. Here you see a table that reflects the performances of GPT 3.5, I believe, that was trained also on tables and then evaluated on this data set that we also use to evaluate this Sherlock model on. Well, we found there that it doesn't reach a performance higher than 0.5. Remember, we had this performance of 0.90 roughly. So that's actually quite a large gap, even with an LLM such as GPT 3.5. And you can then say, okay, but maybe you give it some examples of column type detection, make it more specific. You can tune an LLM to this specific task. Sure, you can do that. You can even provide more specific context, whatever you want, that is specific to semantic type detection, for example. And here, this is the Scores model. This is the bold line here. It reaches a performance close to Sherlock, but it doesn't really beat it, which is interesting. So you have this huge model with billions of parameters, but it doesn't beat Sherlock, which is actually a very tiny neural network, very specialized in this task, but it outperforms GPT. So the bottom line here is you don't always need a huge model for a very specific task. And I think this is what people are now thinking about. How can we move away from these generalist models towards more specialized and domain-specific approaches as well. So there was, you can think, oh, but representation learning, there must be something in that. Yes, there is. So this is an encoder-only model, which basically maps a table to a column vector and then learns some kind of task on that. Now, that was also indeed trained specifically for semantic type detection. And there you see, okay, Turl, which is this model, representation learning model, actually beats Sherlock. Hooray, that's great. But of course, this is comparing like a model from 2022 or something to our tiny model from 2019. And it's actually great that it's making progress, right? Because there is, of course, promise in representation learning, but also in generative models, of course, as well. I'm realizing that, of course, you will come here for data systems and database architectures. So I also did my best to find applications that I haven't been working on, but others have. Because, of course, everyone is really interested in, hey, can I use LLMs or whatever for my task? Also people in the database field. So how can you use representation learning for database architectures? And there are actually some people here, I think, in the audience that have tried to use neural networks for example, cardinality estimation. So trying to estimate the result set size of, for example, a join. And here it turns out that the semantics of columns can help as well. Because what Emmanuel Trumer has recently shown is that if you know what is in a table or in a column, you can better figure out also the correlations between different columns. So there's actually quite some promise in also representation learning for improving data systems in terms of, for example, efficiency. All right. Also, of course, I'm in the DA group. Lots of work on compression as well. And very recently, Kip and Co. have submitted a great paper on compression, namely correlation-aware compression. It's quite basic in the approach taken there, but it's interesting. And I think there's a very interesting way ahead in terms of using like column semantics or at least embeddings for any such tasks. But you can also think about other applications that we've seen today, such as informing data layouts or caching or whatever. But there's like an unexplored terrain, I think. So that's a little bit about the promise of representation learning for data systems, particularly focused on data preparation and transformations and so on. But of course, there are many, many challenges. Many of these like prototypes have been evaluated on very toy data, for example. But we're also interested in making things work in reality, right? So how can we actually make table representation learning work in practice? And now that we have LLMs and we can indeed tune them to our specific tasks, we still see that LLMs are also reaching their limits. And it's more and more becoming awareness that you really need to care about the quality of the data that you feed to these models and the tricks that you apply to make them work for your specific domain. So what data do we then need is the question. So as I said, many research has actually been focused on toy tables, particularly tables from the web, which are quite small actually. But the question is, yes, they are great for web applications, but we all know that web tables are nothing like tables that we see in relational databases. So how do we serve tasks and automate tasks on offline tables? So here we were thinking at the University of Amsterdam, we can maybe take GitHub as a source. And if you then, go to GitHub, you search for CSV files because people love to store tables in CSV files. And you look for the term ID because, people in databases use IDs. You actually find close to 16 million CSV files on GitHub with this term only already. While web tables also typically, for example, contain lots of text, very like understandable tables. Here you see actually some kind of table that resonates more to what we see in real relational databases, right? So you have lots of numbers and IDs. So how do we work with that? That's the question. So what we did is we have been extracting lots of these tables to form a data set. Well, it's not a very exotic pipeline here. You just take CSV files, you parse them. So you should also have a good parser for that that's flexible to capture all the messiness. Anyway, we have annotated these tables, and then we have our great data set that we can train realistic models on. So what do we actually have in GitTables? Well, we have more than 1 million tables, free to use. But I think it's important to note that these tables are actually more representative, not entirely representative, of course. But they are at least much wider and taller than we see in web tables, right? These are tiny tables. We have much larger tables now to work with. And we've shown that you can use this data set to, for example, do schema completion. So given a certain header prefix, what you can now do is you can suggest additional attributes to complement your header with. So that can be quite useful for many applications. For example, knowledge graph enrichment or something like that. GitTables has been widely used in practice already for example, join discovery, CSV parsing, particularly testing them, knowledge graph enhancement, et cetera, But I think it's maybe even more interesting that it kind of set in motion the realization that we need to work towards more representative data sets and that we need to collect them. So I think in the back there's still also who's been developing the schema pal corpus, which also extracted lots of schemas from GitHub, etc. But there's also now more realistic data sets for example, evaluating text-to-SQL models. So SQL, for sure, not for sure, probably is not going to disappear entirely. But with BERT and Spider, we have at least more realistic databases now that we can use to test these systems on. So that's about the data side. But as I said, we also need to have tricks to make these language models. Maybe at some point we should not look at language models anymore, but that's another story. But now we are just on to teaching these language models tricks to understand structured data. So we were wondering, do these table LLMs also capture relational properties? So we have been looking at Codd's relational model. Hopefully that pleases some of you here, to evaluate these language models. So we have this tool called Observatory, and that captures quite some properties according and in line with the relational data model, and then evaluates table models through the embeddings that they generate on column level, on cell level, and on table level. I'll get to a concrete example in a little bit. But by doing that, we can better understand how well they actually reflect or preserve the relational properties that we know tables have. So starting with an example property that I really liked is functional dependencies. So given this table here at the right, we can say that there's a functional dependency between these two columns, country and continent. So what we argue in our tool Observatory is that we can interpret these functional dependency relationships as a translation in the embedding space. I'm not going to go over all the details here, but what we want to understand is if a model preserves these functional dependencies, then the distance between the embeddings of the same pair, so Netherlands and Europe, across different rows should be roughly 0, or at least approximate 0. Here, a bit more intuitively, so maybe those rows and the embeddings kind of shift in the space, but what we say is that the distance here between Netherlands and Europe in row 1 should be the same as Netherlands and Europe in row 2. So yeah, we did that, and now what you can do is you can just take those distances and calculate the variance there and see if that indeed approaches 0 across different models. Okay, long story short, it turns out that most models actually don't preserve functional dependencies. Well, you can think, oh, is that really bad? Well, it can be helpful for quite some applications to actually preserve that. For example, missing value imputation, just saying something. So that might be something to look into for the next generation of table LLMs, let's say. But maybe a straightforward property that is quite important is the insignificance of the order of rows in tables, as well as the order of columns in tables, relational tables, I should say. So what actually turns out is that the way we process the data for these transformer models might not really preserve this property that well, because you just serialize the whole table from a 2D structure to a 1D structure, and then try to learn some patterns there. But if you have, your first row in an entirely different place in another table, your embeddings actually shouldn't change because the meaning hasn't changed, because the order is insignificant. So this is something that we evaluated on as well, and we actually found that many of the models are very sensitive to how the rows and columns are ordered, which is an interesting finding. And we actually also evaluated the impact that this has. So for example, for semantic type detection that we have discussed in the beginning of this talk, we see that by just shuffling the rows, 34% of the generated semantic types changes, which is insane because, of course, nothing about those columns changes actually. So I think there are many, many implications for language models if they don't really reflect the relational properties well enough. So that's about the challenges, a little bit pessimistic, but of course we can do lots of things to actually try to make language models understand tables much better and also be more robust to these different variations. So what I want to end up with, or end on with, is more positive notes towards the future, which I think will be way, way more on end-to-end analysis systems. I know that there is a debate whether you should have all these microservices or be very user-friendly, but I think we should also start thinking about who our actually user will be in 10 years. Will these actually be humans or maybe agents, So these are things that I think we as a community should also be thinking about. Anyway, end-to-end data science. I think quite some people might know AutoML, which is great, right? That tries to find the best machine learning model for any given problem. But end-to-end data science systems should go way, way beyond that. Because data science, as I've shown in the very beginning, that's a very long process that starts with storage, retrieval, etc. So this is what I will be focusing on here. And this is Google's data science agent. And you can see that with a given prompt, it just automates every single step in that whole pipeline. Right? I'm not saying it's very robust. I'm also not saying that the answer will always be correct, but this is where things are going. And I think that's just fascinating. Now, I hope you will be relieved that actually under this, there's lots of like code generation, also SQL generation. So when people are saying that SQL is going to die because of our natural language interfaces, it doesn't mean that SQL is going to die. It's just a different abstraction that we build on top of it to make it more user-friendly. So yeah, this is more like code generation based. You also have people now that are focused on building agents for graphical user interfaces. Well, I wouldn't take this direction. But of course, there are so many different tools that we currently have that might not have very good APIs, for example. They might need such data science agent that works on graphical user interfaces. I think the question for us to think about is, what's the right level of abstraction for data agents to operate on? And should systems even still focus on humans, or at some point also really embrace agents as their customer? So, okay, I think that sounds pretty cool, or at least to me. The question is, how do we get there? And I think, and this is actually quite surprising to me, that for data systems, one thing has always been very difficult, somehow, is the search functionality. So one very important part of all these pipelines is the retrieval phase. So here, I think that's like one of the first steps in such pipeline, how to find the right data. And whoever or whatever is trying to find that data, we do need to find it in the first place. So yeah, as I said, I'm super surprised that this is still not an easy task, even if you're a data scientist, whether you want to use Snowflake or Databricks or whatever. It was a process that took like weeks to find the right data set. And even I know that Snowflake is now merged with Neeva, and I hope there will be some interesting improvements on this end. But this is really a big problem. I won't bore you with some data search approach that we are working on as well. I just want to focus on how LLMs or agents or whatever are going to retrieve the right data. So talking about the kind of questions that we are asking, well, this question here might not really look or sound familiar to you, but what's the highest eligible free rate for K-12 students? Very specific to the US. Fortunately, we have ChatGPT, and ChatGPT knows exactly what is meant in this question. So that's great, but it still has this very long response that it generated. I just want to highlight one specific thing in this response, and that is you generally need data from specific districts or schools in the area. Yes, that's no surprise. So I think this is where retrieval augmented generation comes in, to retrieve the relevant data for this question. Okay, great. So we're going to look into RAG to answer this question. What I am really surprised about, actually, is that what people have been trying to do in RAG land is try to fetch data from knowledge bases or images or documents or whatever. But no one really has been thinking about relational data. Well, relational data has lots of fresh domain structured data, right? So it's a great source for retrieval augmented generation for answering such questions as well. So this is what I've been looking into, and indeed, if you tie this question answering system with your relational database, given that it has the relevant data, of course, you can actually answer this query much more easily. So I will give you a few examples of questions that you might be asking that involves relational data. So for example, which urban Japanese prefecture is not associated with thorny trees? Apparently there's some data that stores that in a table. Other questions, I think it's interesting to note that many of these questions actually involve aggregations, not only lookups, but also comparisons, etc. So yeah, great use case for structured data. What does such a pipeline look like? Well, first we contextualize and interpret the query. We then retrieve the data. We generate some answer, and we're happy. What people have been looking into a lot is this interpretation step of the queries. Also, lots of work done on the generation. For example, generating SQL code. Perfect. But we're really missing a crucial step here, and that is how we actually need to retrieve structured data. There's no research on that that has been exploiting, the capabilities of LLMs today. So, yeah, as I said, retrieval is super difficult, but it's also crucial. As Wenu put nicely on Twitter at some point, for any good RAG system, it might be very good, but if your retrieval is mediocre, you can easily distract your LLMs, and you will end up nowhere. So there's also still a very long way to go to make this work for structured data. I'll hurry up a little bit. What does that look like? How does that work? Well, you have your set of tables. Then you want to embed all those tables in there. You embed your query. Then you do some similarity search, basically comparing your vector representation of your query and your vector representation of your tables. And then you retrieve the top k relevant tables. Okay. The question is, given the existing approaches, which are quite basic at the moment, we don't really know how effective these are. So what we then do is, of course, build a benchmark for it. So we built Target at Berkeley, and this is actually a benchmark to evaluate retrieval of tables for downstream generative tasks. SQL generation, we have question answering, and fact verification as well. It's very easy. We just take all the data sets out there for these different tasks. We have a bunch of retrievers integrated. We have a generator, very simple prompts. Just, given this table, generate me the answer. And then we have our evaluations consistent with the metrics used or proposed for these data sets and tasks. So what are the insights? Well, surprisingly, or maybe not surprisingly, BM25, I'm not going into the very specific details there, but it's based on lexical comparisons and frequencies in documents or tables. Much less effective for structured data compared to text. So in RAG over text, BM25 is always considered a robust baseline. For structured data, it's completely different. You don't come anywhere with BM25 or TF-IDF kind of approaches. Of course, there's also OpenAI. We can just embed our table with some huge model and also embed our query and then do the similarity lookup there. Yeah, that works. Works fine. Interestingly there, I think, is when you also embed rows of your table, actually the performance of the retrieval drops. I found that quite surprising, but if you think about it, just adding more data to your embedding just distracts the signal from those embeddings. So I think there's work to do to make that better, or at least figure out what then the best configuration is for this. All right, these are some other small notes. But there's much to explore. For example, what is the right input, right? What should we actually feed into these LLMs? But also, how do we then route, our query to the proper data source? Because we cannot always use relational tables as much as we wanted to. Sometimes we also need to use knowledge graphs or documents or whatever. And then something that I'm really excited about is that in practice and in reality, things are just much harder. So how do methods actually perform on more challenging tasks and data sets? But also, how can we close the semantic gap between the input queries and the documents being tables for retrieval systems? Now, as you know, and as you've been focusing on, tables and databases can be huge. How do we deal with that? And for example, how can we do in-database table retrieval as well, besides of database retrieval, for example? But even going a step further in a more hierarchical way, if we have our table, it might be too large. So we need to select the relevant rows, relevant columns, etc. And this is, of course, what we have in mind to extend targets on as well. All right, wrapping up just in time for Martin's great award speech, of course. Some key takeaways that I hope you will leave today's talk with is that, of course, relational data is prevailing in the data landscape, especially in enterprises, so we should deal with them and use them to the maximum potential. There are actually very interesting capabilities of foundation models for also relational databases, so I'm super excited about that. I don't have to repeat probably, but tables are not natural language. There's very specific properties about tables that we should be working with. But to do that well, we need the right data. We need the right skills also, or the right tricks to adapt these models to structured data. And then perhaps a thinking or a thought that you can end on with this day with is that I really think that we're moving towards a more agentic kind of pipelines. So we need to think about how we are going to design these systems also with that in mind. And there, I think retrieval is really key. So we should also be improving our search capabilities this time for sure. All right, and that's it. Thank you.